We have Roghayeh Maleki. She'll tell us about on standard integral table algebras with integral multiplicities and non-cyclotomic character values.
Thank you, Andy. And I would like to thank the organizers for giving me this opportunity to present my work, and I'm so blessed for your attendance in my presentation. All right, so today I'm going to talk about standard integral table algebra with integral multiplicities and non-cyclotomic character values, and this is a joint work with Alan Herman. So, in fact, the purpose of this talk is to answer the cyclotomic eigenvalue question for commutative association scheme, which was posed by Simon Norton in our conference in 1980. And in reality, this is a question in Ghana, it was booked in 1984. Okay, some background information. First of all, the association scheme. So we have a set of non-zero, set of n by n 0,1 matrices, A0 up to AD, that satisfy the following property. First of all, the identity matrix is inside and they all sum to the all one matrix. And it is transpose closed, and the multiplication of two elements lie in the span of the set A. And also because it is commutative, so the multiplication AI AJ equals AJ AI for all indices IJ in the set 0 to D. And now we say let A be an R-dimensional algebra with a scalar linear involution star over the complex C. And the pair AB is called integral table algebra with finite basis B if it satisfies the following properties. First of all, the identity matrix must be inside these bases. And then the basis is star closed, and we have the structure constants of the bases of the algebra that are obtained by multiplication of two basis elements. These are the structure constants, these coefficients, and since we are talking about integral table algebra, these coefficients, in fact, must be non-negative integers. And then the last property is the pseudo-inverse condition for the table algebras. Okay, so we have some remarks here. First of all, every table algebra has a star algebra homomorphism delta that takes each basis element Bi to delta of Bi, which is in fact the maximum eigenvalue of each matrix Bi. And then we say the basis is standard when for each basis element we have this identity that the degree of each basis element is in fact lambda I star 0. I star 0. Therefore, we can say that every table algebra has a standard basis. Even if it doesn't have, we can rescale each basis element and get the standard basis as well. And then, as an example of table algebras, we refer to GSCC algebras of the association schemes, which obviously has the standard basis. Then we have a representation chi of the algebra, which is a homomorphism of this form from the algebra to the matrix algebra over the complex numbers. And this representation, the character afforded by this representation is denoted by chi, and is defined to be chi of Bi is the trace of the image of each basis element under this representation. So we take the trace of the image of each basis element, and it is in fact the character afforded by this representation. Okay, now we have the description of the character table. We need to be familiar with this character table because the proof is in fact depends heavily on this character table. So first of all, what we have in this character table, we have reducible characters of the algebra, and then on top we have the matrices of the bases, and then on right hand side we have the multiplicities of each character, and inside we have these elements which are in fact the spectrum of each matrix Bi. And the first row that are denoted by red color are the largest eigenvalue of each matrix Bi. So our table algebra is in fact here commutative. We must note that. And so we say that the standard table algebra basis determines a standard feasible trace row that is denoted by this function. which is a positive linear combination of irreducible characters. And then the table algebras have a standard representation if and only if these multiplicities, that is, appears in this relation, are positive integers. And since association schemes have the standard representation, so for them, these multiplicities must be positive integers. So these are the facts that we use in our proof. And so I think now we are ready to state our main problem, which is cyclotomic eigenvalue question. So the question is, if all entries of the character table of a commutative association scheme is cyclotomic, or we can say that, is there any association scheme for which the character table has some values that not all lie in the cyclotomic number field? So as a previous work in 2011, this is almost a new topic. So in 2011, Herman and Rahmani-Baravi, they proved that this question is true for Shorten association scheme and commutative quadratic schemes. But my answer to this question is, I used a character table of a standard integral table algebra with integral multiplicities, and I was able to show that up to rank 4, the answer to this question is yes. But in this presentation, I'm just going to focus on rank 4 because we don't have that much time to go over the rank 2, 3, or more than that. So we have some preliminary results. First of all, we have a lemma. If we consider a table algebra with finite basis B, we have this identity here that is obtained by a condition which is obtained by the associativity of the multiplication, because when you multiply basis elements, and this is the proof is almost very long and complicated, so I avoided to talk about the proof here, but in fact, it comes from this associativity of the multiplication that we can have this identity over the structure constants of the algebra. And now we have the proposition that says that, in fact, this proposition is talking about the property of the regular matrices that we have in the basis, that says that for each basis element that we consider, the gross sum is a constant and it is equal to the degree of each basis element. So again, some more remarks here. The splitting field of a commutative integral table algebra is in fact the smallest field extension K over the rational that contains all the character values in the character table. And we say that this field extension is Galois if we have this equality, the size of the Galois group is equal to the dimension of the extension, in fact. And so also we know that the Galois group acts faithfully on the row of the character tables. And we say that every cyclotomic field is a Abelian Galois extension over the rationals. And at the end, we talk about the Kronecker-Weber theorem that says that every abelian extension of rational numbers Q is contained in a cyclotomic field extension. So we use all these tools to prove our main theorem later. And as a last theorem in this section, we consider a set H of the Galois group that acts, in fact, on the columns of the character table and permutes the columns of the character table. In this case, we say that this set is, in fact, the subgroup of the Galois group, and it is, in fact, in the center of the group. So I think now we are ready to talk about our main theorem, which is about rank 4 standard integral table algebra with integral multiplicities. And we want to say that they have cyclotomic eigenvalue character table. Okay, the proof is in fact by contradiction. So first of all, we let P tilde be the character table of rank 2 association scheme, and it has this character table of this form. And The rank 4 standard integral table algebras with integral multiplicities of order n are in fact commutative functions of rank 2 in P tilde. You go back to P tilde and you break in fact bi into pieces, you arrive to this character table for rank 4. But we want to know what are the matrices inside and what are these values, so we'll talk about it. So first of all, we assume that we have a noncyclotomic eigenvalue in this character table. Let me just go back here. As I explained before, these are the spectrum of each matrix Pi. So I suppose that there is a noncyclotomic character value inside. Let's say alpha 1 corresponds to the matrix P1. But then by Kronecker-Weber theorem, the splitting field of the Galois group, the splitting field has to have the Galois group which is non-abelian because of this theorem, because we suppose that one of the eigenvalues is noncyclotomic. And then we computed the minimal polynomial of the matrix P1, which is of this form, which is not irreducible in fact over the rational, because this P1 is in fact in Q itself. And it is the largest eigenvalue of the matrix P1, and we suppose that they are all integral. And then we say that the minimal polynomial of alpha 1 is of this form. So it has degree 3. And so since the splitting field of the algebra is of this form, and the minimal polynomial has degree 3, then we say that the size of the Galois group is in fact equal to 6. So the Galois group should be either C6 or Sim3. But before, in the beginning, we suppose that the Galois group, we obtained to this fact that if one of the eigenvalues is non-cyclotomic, the Galois group must be non-abelian. So in this case, the Galois group can't be C6. So we arrive to this fact, the Galois group is Sim3. And also we say that the non-trivial in this character table are all equals and equal to M. The reason that we say that these multiplicities are all the same is because the Galois group acts faithfully on the rows of the character table. And so if they are not equal, so the Galois group will permute them. But this contradicts the fact that the Galois group fixes the rationals. And these are, we suppose in the beginning that the multiplicities are integrals. So they must be fixed by the Galois group. So that's why we concluded that they must be all the same. And then by column orthogonality condition, we have this relation that leads to this identity that the degree of each matrix element must be equal to n. This is like, we need to do some computation here to arrive to this identity. So in fact, the character table will be of this form. We have the same multiplicities and the same degrees for each basis element. And now we want to realize what are the matrices in the basis. So the matrices are of this form, but you might think why some of the columns in these matrices are the same. For example, for B1 and B2. And this, in fact, comes from the commutativity of the algebra, because we have Bi Bj equals Bj Bi. And for example, here, Bi Bj equals to sum over k lambda I jk. Okay, these coefficients here are in fact entries inside. So when, for example, this column is B1, B2, this yellow color, and this yellow color is B2, B1. So we have the commutativity of the algebra here. So these are the coefficients that appears in this multiplication, so they all must be the same. So, and then...
yeah, excuse me. Would it
yes.
be possible to just give a brief summary of the main conclusions of the rest? We're actually at the 15-minute mark now.
Okay, sorry, yeah.
That's okay.
And so, so we consider all these identities and relations and these matrices of the algebra, and we arrive to the set of the identities. When we apply them on the matrices, we note that these matrices are in fact permuted and they are conjugate of each other. So when they are conjugate of each other, they have the same characteristic polynomial, and so the columns are permuted by theorem that I mentioned in the beginning. So the Galois group is central. That means that the Galois group is abelian, but this is contradictory to our first assumption that we say that the Galois group is non-abelian. So therefore, the character table will be always cyclotomic. Yeah, that was everything that I wanted to talk today. Thank you. Thank you.
Okay, do we have any questions? So you said you proved this up through dimension 4, right?
Yes, and I was able to work on more steps on dimension 5 as well, but because we didn't have time, so I didn't go through that one.
Okay. Is it something that you think you'll be able to, like, do you think it'll be possible to prove something for all dimensions, or is this something where just each case gets more complicated as you go up?
Yeah, you're right. Each case will get more complicated because up to rank 5, I think I found an example that says that for rank 5, the character table is non-cyclotomic. But for rank 6, the basis is getting bigger and bigger. So finding the variables in each matrix is really complicated. And even if you use the Grenoble basis, it takes maybe a week to compute these entries in the matrices.
So you said for rank 5, it's not cyclotomic at all.
It is not cyclotomic.
Does that contradict that conjecture?
No, I mean, sorry. For rank 5, I found an example that says that the character table is not cyclotomic. So I can't say that for rank 5, we have always the cyclotomic character table.
Okay, interesting.
Yeah.
Other questions? We have about 2 more minutes.
This is a little bit tangential to your talk, but you mentioned that the structure constants of the table algebra are always positive integers. And that makes me wonder if there's a combinatorial story about what they're counting.
In this case, when I'm talking about the standard integral table algebras with integral multiplicities, the structure constants should be always positive integers. But they might be negative in some other cases.
Oh, I see. Okay.
Yeah.
Okay, let's thank our speaker again. Nice job.
Thank you.